So today we're going to start a video here for you to finish off your notes for Ecology 2. The reason I'm doing this is so that you can listen to the rest of the lecture at your own leisure and be able to stop and start as needed so you can fill in your Ecology 2 notes. Now you may or may not be able to use these notes while you're taking the test. So we've discussed how energy enters an ecosystem through the primary producers down here. The use of ecological pyramids supports what we've talked about with food chains and food webs. The reason it looks like a pyramid is because of the 10% rule, where it states that of all the energy that an organism will consume in its lifetime, or produce if you're a producer, that 90% of that energy is going to be used to live, to make new tissues and things like that. Those life processes. A lot of that energy is also lost as heat. So only about 10% of the energy that an organism has consumed in its lifetime is available for the next trophic level when it gets consumed itself. So energy pyramids show this dynamic. And the reason we use a pyramid is that you need a larger base on the bottom to support smaller levels on top. Now the nice thing about this energy pyramid and the 10% rule is that when you move from one stage up to another stage, from producers up to primary consumers and so on, that only 10% of the energy moves on. So the math is actually quite easy. As we see, these kilocalories is a unit of energy. And when we move from a producer to a primary consumer, we take that decimal point and just move it over one spot. Same thing from the primary consumer on up. So we go from 100 up to 10, and then 10 up to 1. So essentially, of all of the energy, 100% of the energy that the producers have converted from light energy into that molecule form from taking CO2 plus water and adding in light energy and then creating our glucose molecule C6H12O6 and oxygen, that photosynthesis, that only 10% moves on. So you move that over one spot and you get 10%. And then over one more spot, 1%. And over one more, 0.1%. So again, here we have 2,000 units of energy available. So if there's 2,000 units of energy to the producers and plants, and make sure that you look at this. You move up. So then as you move up, we go to 200, 20, 2, and 0.2. Now this is not to say that if you eat a hawk versus a snail, you are only going to get 0.2 units of energy to 200 units of energy of the snail. What this says is that of the 100% of the energy that the producers converted from sunlight into molecules, that only 0.2 or 10, 1, 0.1, 0.01% of that energy is remaining. This is why a lot less of your top level consumers can be supported than the levels below. And so here we see the answer. So a biomass pyramid literally means the amount of living tissue. Bio meaning life and mass meaning stuff. Since energy is directly related to the amount of work that can be done, the amount of cellular tissue that you can produce is based upon the amount of energy available. So we again see this pyramid level where you need more producers than primary consumers, and then secondary consumers, and then tertiary consumers. Pyramid of numbers can look different. And the reason that this can is because we're looking at straight numbers. We're not looking at energy, we're not looking at biomass, just counting individuals. Now, when producers are small, it does take a lot of producers to provide that amount of biomass and energy to the upper levels. But when your producer is extraordinarily large, like an oak tree, that can support a large number of insects and then birds on top of that. But if we were to look at the biomass of that oak tree versus the biomass of the insects, it would be back to that traditional pyramid shape. Now here's biological magnification. We discussed this briefly when you guys did the active read the other day. So as we see, this chemical DDT in water is at a very, very low percentage, 0.000003 parts per million. Now what happens is as these zooplankton are filter feeding water, some of these chemicals get stuck in their body tissues. And as they get stuck in the body tissues, then when they are consumed by these smaller fish, that fish is processing the materials of those zooplankton, but those particular chemicals are getting trapped in their tissues, and then so on up and up. So by the time we get to a top level consumer, that percentage or part per million has gone up incredibly. Now, not all molecules do this, but there are a lot of toxins where this will happen. Now, getting to the heart of how ecosystems work is the difference between matter and energy. So matter is recycled, and that's based upon the idea that nothing is ever created or destroyed, just transformed into different configurations. And we see that again with the photosynthesis equation, where you are taking CO2 and oxygen and then using that light to rearrange those molecules into a sugar, glucose, C6H12O6, and oxygen. So we have not created or destroyed any of the carbons, hydrogens, or oxygens, but what we have done is, H2O, is rearrange them, transform them. Now energy, that is always flowing through an ecosystem. So it enters into this through this equation and then will stay there until it is released. As we break these molecules, as consumers, we take in the C6H12O6, the sugars and oxygen, we break them apart and we release the water and the CO2, and energy is released as well. So energy flows. It's like a river turning a water wheel. So the water is the energy. The wheel is matter. So matter is constantly being recycled, moved around. These atoms are moving around the earth in these bio, meaning life, geo, meaning earth, chemical, meaning stuff, and then cycles. Now that's not to say that things can't get stuck at certain stages and build up, but it's being moved around constantly. The various cycles. Water cycle is your basic cycle. Now the driver of this is, of course, the sun. The sun is what is providing the energy necessary to take the water from a liquid phase up into a gaseous phase. And then it's the sun's uneven heating of the earth which creates our global wind patterns to move those clouds over to land. This is when gravity takes over and forces that water down. Now as it comes down, it will start to dissolve minerals from the rocks and the soil, and it will also erode. Now this is what keeps other minerals cycling through this ecosystem as well. But that main energy source for that cycle is again the earth and then gravity. There is another process called transpiration to bring water to the air. So trans means to go through. This is when water travels through the roots of trees, through the leaves, and then back into that gaseous form. Carbon is one of those critical molecules for life. We are called carbon-based life forms because carbon forms the central molecule for all of life's molecules. It is a very flexible molecule, the Swiss Army molecule. It can form 4 single bonds. It can form double bonds like in CO2. It can form triple bonds as in carbon monoxide, CO. It can make the softest components like graphite that you use in your lead to some of the hardest chemicals on the molecules on the planet and substances as diamonds. And diamond is a pure carbon with single bond with other carbons. A very pure diamond will have all carbon bonds, and some of the impure diamonds will have other molecules. So carbon moves through this cycle through photosynthesis and respiration. So photosynthesis was taking carbon dioxide and making that sugar, and then respiration is taking that sugar and breaking it apart. There are longer and deeper cycles, and this is called deposition. So deposition is when carbon will get deposited into the earth. Now this happened about 200 to 400 million years ago with massive organic growth, lots of plants and animals growing and so much dying that there was not enough decomposers to keep up. So these dead plants and animal matter were deposited and then over millions of years through the pressure of the earth converted into our fossil fuels. Now eventually we have been taking those and adding them into the atmosphere when they normally would have over normal geologic processes taking hundreds of thousands to millions of years, and we have sped that cycle up. Another main element that we need is nitrogen, and nitrogen is used a lot in amino acids. So amino acids are the building blocks of proteins, one of the key biomolecules we will talk about next unit. So these proteins are the little machines that do everything to keep you alive. Me talking and moving right now is based on proteins. The food I've eaten being broken down is based on proteins. Now, most of the nitrogen is found in the atmosphere. 80% of our air is nitrogen. It is a diatomic molecule, di meaning two and atoms, so nitrogen bound with itself. Now, in this form, it is unusable. We breathe it in, we breathe it out. To put it into the usable ammonium form or nitrate form, the key here is bacteria. Bacteria do the job of pulling the nitrogen out of the air and converting it. Now there are special relationships with these legumes that they provide a space for the bacteria to live, and bacteria then provide nitrogen, which allows the plant to grow even better. Decomposers also extract nitrogen from plants and animals that have died. There is another source of nitrogen, and that is lightning strikes. When a lightning strike forms, nitrates and nitrites can also form. Now to put the nitrogen back into the atmosphere, again, it is bacteria that do the key of converting these nitrites and nitrates back into that diatomic nitrogen into gas. Phosphorus is another element that we need, and phosphorus is used heavily in the structures of DNA and RNA that we will see next semester. So phosphorus is found in a lot of these rocks. It's a mineral that gets incorporated when rocks are created, and this is where water's role as the universal solvent has played a big key. As rain runs over these rocks and weathers them, it can dissolve and pull that phosphate out of the ground, out of those rocks. So when it becomes in the soil, plants will take it up, and so then the animals will also eat it. And again, as they die and decompose, that phosphorus is also added to the soil. So we've looked at four of the basic cycles of molecules as they cycle through the environment, from water, carbon, nitrogen, and phosphorus. It's not limited to just those nutrients, but those are the four basic ones. So when we look at each type of ecosystem, there is a thing called a primary productivity, dealing with the primary consumer, or the primary producers, the organisms that are capturing that light and converting it into a molecule, glucose, that C6H12O6. So the amount of sugar that they can make, which is measured in this billions of kilocalories per year. So calories being a unit of energy. You have sugars and drinks, there you have calories. It's dependent upon how much light that ecosystem receives, but also the nutrients needed to produce these molecules, to grow the organisms that are going to produce these. So if we see the open ocean, tropical rainforest, temperate forests, they are the most productive in producing units of energy in chemical form. And as we go down, the desert is baked in sun, but water is a limiting nutrient. Now there are the other nutrients, that carbon, the hydrogen, the oxygen, nitrogen, phosphorus, sulfur, the basic elements that living things need, and then there's other small ones. So it's not necessarily the nutrient that is in limit, is not necessarily the least amount, because you may need much more hydrogen than you need phosphorus. It's just that that percent that it needs is in a low amount. So this limiting nutrient is what sets the max amount of productivity. So you may have an excess of all of these other elements, but if nitrogen is in a low supply, no matter having as much of these others that you need, nitrogen is the lowest amount. So that's like your track team is only as fast as your slowest person. So if limiting nutrients are setting the basement for what a ecosystem can produce, if you increase those limiting nutrients, you can then produce more calories, more materials, more biomass, and more tissue. Farmers do this and add them to the soil so they can increase that productivity. Soil is naturally low in that nitrogen, phosphorus, and potassium. So by adding these basic elements in fertilizers, those nutrients will be added to the soil and then raises that ceiling of what can be produced. If you can remember the story we were told growing up of how Native Americans told the Pilgrims to put a fish when they planted corn. As that fish would decompose and that nitrogen, phosphorus, and potassium would be added to the soil, those crops would grow better. In the oceans, nitrogen is a limiting nutrient, and then in these freshwater ecosystems, lakes, rivers, streams, it's phosphorus. Now, what happens normally is that when farmers add this, those nutrients don't stay in that one place. So in these water ecosystems, when it rains and that runoff then goes and travels down these rivers and streams, that boost of that limiting nutrient, of that phosphorus that was in a short supply, then raises that primary productivity very quickly. Now, algae, a very simple organism that can grow very, very, very quickly, utilizes that boost to have a bloom. So it grows very quickly, much faster than the other plants, animals around it. So what that does is when it covers this lake with an algal bloom, that would cut off then the sunlight from hitting that lake, from getting down to the bottom where there's plants down there that would utilize that sunlight to photosynthesize. That causes a drop in oxygen levels that they would be producing inside the water, which then leads to a fish kill. This is what we simulated in our eagle population lab in that fifth data table with a phosphate pollution. That algal bloom grew, blocked out the sun, causing a massive fish kill, which then affected all of the other animals above it that relied on that. So now we get to community interactions. So remember, community interactions is when you have two different species or multiple different species. So this is that level above the population, or population is a single species. So what we see is competition, where you have organisms using a same resource, and it could be a place, it could be a food source, it could be a water source. Then we also have predation, where an organism is eating another organism, or herbivory, where you have an animal eating a plant. And plants will do a lot to protect themselves. They produce spines and needles, they make toxins. So plants are not passive in this, they are actively working to protect themselves, or sometimes they're utilizing those. And that's where we get to symbiosis. So sym means together. Bio, we know, means life, and cis is the condition. So these are two species that live closely together, and we're going to focus on the symbiotic relationships. So the three symbiotic relationships can be demonstrated with plus, minus, and a zero, which means nothing. So in the mutualistic, it means it's a mutually beneficial relationship. They both get a positive out of it. So the clownfish here is getting a home. The sea anemone has stinging nettles, and so other fish and predators do not want to get near there. They will get hurt by that sea anemone. Now the sea anemone out of this relationship is going to get a cleaner, essentially. So as we saw in Finding Nemo, that Marlin, the father, was sitting in that anemone, and that's usually the case, that the males are doing that, and they are keeping it very clean, getting rid of parasites, and they're attracting a female partner by showing them how clean they can keep their house. So actually, if there was a damaged egg, a real clownfish would have gotten rid of it or eaten it to get rid of the mess. So Marlin would have eaten Nemo. So we see a lot of mutually beneficial relationships between bees and flowers. We saw that in the video with the bee is getting that sweet nectar that's going to convert into honey. It's getting food. And then the flower is getting help in reproducing with that bee visiting another flower and bringing that pollen to another flower. On the opposite end of the spectrum, we get the parasites, where the parasites are getting food. If they're sucking blood, blood is just basically a shake of liquid nutrients. Very easy to digest, so it gets a bunch of nutrients. On the other hand, the other organism is not zero, but harmed. They actually get a negative. It hurts them. Sometimes those parasites are bringing other diseases. Um, they are harming their host in some way. So we see that with a lot of the fleas and ticks and lice and leeches. So that's that parasite. Commensalism is the weird one. That's where one does get a benefit, but the other one really doesn't care. There is no harm done, but there is no benefit either. So the most common that we see would be these barnacles on a whale. The barnacles are these little guys that are all over. So a barnacle is actually a crustacean. It's a shrimp that has changed its bodies to be stuck somewhere and filter feed, like other crustaceans would do. Now the thing is, a whale that has a bunch of barnacles like this one, or a whale that has none, they have basically equal fitness. They have an equal ability to survive. It doesn't weigh them down, it doesn't slow them down, they're so big. It's no problem. The barnacle, on the other hand, does get a benefit. If it wasn't stuck to a whale, it'd be stuck to a rock. And that means it would stay in one place. And so the food has to come to the barnacle. It would have to filter enough water and get the nutrients out of it. So if there's no food there, they're out of luck. By being attached to a whale, that means it gets a free ride. It gets access to more ecosystems and a wider variety of food, and thus it is healthier. So now when we have an individual population, we want to look at the things that can affect that population. So I like to think of a population then as kind of a balloon. Now, things that make that balloon bigger and things that make that balloon smaller. So these first two are obvious. Birth rate, where if there's more individuals being born, whether it's plants that are growing and producing seeds or an animal having kids, whatever it is, birth rate would increase that balloon by adding more air and get larger. And then death rate, organisms dying, would definitely make that get smaller. The other two, immigration and emigration, well, they come into play when we are looking at a population in a particular location. So there's a boundary. So if we're dealing with global, like the global population of humans, there's no one entering and leaving the planet necessarily. The space station individuals are just hovering around it, but they're not leaving and entering. So global populations only deal with birth rate and death rate. When we're dealing with a location, a defined boundary, and we can look at Lafayette, Indiana, we have individuals that will immigrate, that will enter into a population and then add to that population there. So they've left one location and entered another. Emigration is when you leave a population. So immigrate means to leave, and you want to think of emit, starts with an E. Now they both sound the same, immigration, emigration. We try to pronounce immigration, so pronounce the I and for emigration. You should be able to predict what would happen to a population. So I like to use, again, that circle to do the work for me. So we have an increased birth rate. So I draw, a fairly large arrow to show that they have a larger or an increase of birth. And a death rate is decreasing, so that's a much smaller arrow. So we put those arrows side by side, so the births versus the deaths, the net change shows overall is going to be positive. So we would see that this population up here would be increasing over time. So then the next one, if we look at a increase in birth and also an increase in immigrants, those are two things that are both entering that population and causing them to increase. So they will compound each other and we'll see a massive population growth. So here we have then in this third option, we have an increase in the a decrease in the birth rate. So we have a smaller arrow going in and a larger arrow leaving. So if we have very few entering, but then quite a few leaving, that net change shows that that population will be decreasing over size. And if the birth rate and death rate are equal, we should have a steady state. So that's what we would see. The population would remain the same there. So when we look at growth curves over time, what happens to the size of our population? Well, in exponential growth, if you have plenty of space, plenty of food, no predators or low predators, low disease, there's nothing that's limiting that population. That population is going to grow very quickly. So we see this term exponent, exponential. So an exponent, we say x to the y. So the y is the exponent. And if we want to grow that exponent, so let's take the number 2. So 2 to the 0 is equal to 1. Anything to the 0 power is equal to 1. And we grow that exponent. Well, 2 to the first equals 2, and 2 to the second equals 4, and 2 to the third equals 8, and 2 to the fourth equals 16. And so as we keep growing this exponent down, we keep doubling. 16 to 32 to 64 to 128, 256, 512, 1024, 2048, and so on. So instead of looking at time and numbers, and we graphed exponent and the result, no matter what number, 2, 5, 7, a billion, the numbers would change on our scale, but they would all look exactly like this. They would all have that exponential growth. And in fact, every organism would grow exponentially given these conditions of space, food, predators, and disease, no matter how quickly it takes to reproduce. With a bacteria that can reproduce a new generation every 20 minutes. When you look at an elephant can take 30 years for a baby elephant to grow up and have its own kids. Given enough time and without any restrictions of space and food, predators, that elephant would also grow exponentially. Now that can't happen in all cases. So this is where we see logistic growth, the logical growth model for organisms. So we do see a beginning of exponential growth. When we are at a low population down here, there's plenty of food and space. And so we see it start to grow in this exponential manner. Low growth, then it starts to grow exponentially. Now, as this population gets larger, then we see this growth beginning to slow down as food and resources become less available. We see an increase in competition for those resources, and eventually we hit this steady state right here. That steady state is called K, carrying capacity. It's that largest number of individuals that an environment can support, and it can support what we call indefinitely. It is not defined. Forever, essentially. That the amount of resources that are used by this organism, consumed, will be recycled within a year. The amount of water that it uses is what falls annually in that area. Leafcutter ants. Some leafcutter colonies can take up to 25% of the vegetation in a forest, but that's what would grow back in that year. Now, could a population grow larger than the carrying capacity? It can. In a short-term situation, yeah, you could grow much more. Leafcutter ants could, instead of eating 25%, eat 50% of the vegetation. It's there, they could eat it. But what would happen is that those leaves would then not grow back as quickly, there'd be less available, and eventually there's a check, and we see it drop below. So in real life, we don't see populations really hit this curve. In reality, it gets much more messy, where you go, oh no, it's tough, and then up and down, and it kind of hovers around that line. Some years of better growth, and then there's some leaner years because resources are overused. And the K value is not set in stone either. The K value can move up or down depending upon factors within that population, a change in climate, introduction of a new species. But theoretically, this is the relationship between the environment and the organisms within there. So, there are things that limit populations from growing too largely. And they are broken down into two categories. Those that depend upon density and those that are independent of density. So density is a measure of weight, so in grams, over volume, milliliters or cubic centimeters. So you have an object that weighs a certain amount and it takes up a certain amount of space. When we look at density of populations, we look at an area and the number of individuals that live in that area. So you can have a dense population with a lot of individuals. Think at mega cities, millions of people, versus another area of the same size where people are not so closely populated. And this could be not just people, we're talking animals, we're talking plants, bacteria, all sorts of things. So the factor that prevents populations from growing, that becomes into play as you reach that carrying capacity, broken down into either being dependent upon density or independent. So if you depend upon density, you depend upon this situation to either become a factor or have a greater impact. These factors can also affect a low dense population, but they're not as critical. Now, independent means that you don't care. Both of these populations can be affected equally. So, we look at those density dependent factors. These things, the competition, predation, parasites, stress, a dense population will be affected by these more, or they come into play more. If there's more individuals in an area, it becomes crowded. They're competing for the available resources. If you're a predator and you're eating an animal, you're going to go for the thing that is most dense, the easiest to find. If you're an owl and you've got moles and voles and mice, chipmunks, rats, other birds, snakes, this whole food web, you're going to go hunting for the easiest prey, and the easiest prey will be the one that you see the most often, the most dense. So that predator, the owl, is keeping that population from becoming too dense because they become a food source. Parasites and diseases. So traveling, going from one organism to another, infecting them, the mode of transmission. If those organisms are closely together, they're easier to be passed between them versus if they're farther spread out. And then you get that stress from overcrowding. So these depend upon density. When you're trying to think about it, think about, okay, if I have an extraordinarily dense population, lots of individuals, lots of trees in an area, lots of grasses, lots of funguses, animals, whatever it is, and I compare it to an area that's very sparsely populated. And if you can say, okay, there's going to be greater competition here than there is here, well, then that depends upon density. If I'm a predator and I'm going to be easier to eat in this dense area, that depends upon density. A parasite, more easily passed. So when we look at independent factors and we look at those same situations, really densely populated versus sparsely densely populated, and we say, well, they're treated equally, it doesn't really matter, then that is independent of density. A drought, does a drought care how many individuals are there? No, it's not getting water. There's no water available. A hurricane, well, hurricanes are hurricanes. They just be hurricanes. We're seeing an increased amount of damage from hurricanes. Well, that's because we're there. They would be there without us. Now they may not be as intense because of adding excess heat, adding more energy to those storms, but these things are so big and they're not affected by density. Well, this is the end of my presentation. Thank you for listening. I hope this was helpful. Please feel free to shoot me an email or write me a letter if there's anything that I can do to improve upon this, as this is my first time. You can rewind, watch it again, just for fun. Pop a bag of popcorn, sit down with your family, and listen to the wonderful presentation. But in sincerity, I hope that this helps you prepare for the test. These notes should hopefully be helpful on the test, as again, you may or may not be able to use these for a period of time on the test. Wink, wink. Good luck, and I'll see you in class.